there, folks. Back here with what I would say maybe is our last video or a little lecture here on the case for derivatives of specific function types. I do have a few more things that I probably want to show you in a couple more videos that you might appreciate with respect to the derivative. But with respect to derivatives of different function types, this video is the last case we're going to take a look at here. And that is the derivatives for the inverse trigonometric functions. Let me bring my notes up on this. All right. If we remember, the inverse trigonometric functions are in a relationship with their corresponding trigonometric functions in a inverse behavior, right? Such that y is equal to f of x if and only if x is equal to, or x is equal to the f inverse of y for our specific inverse trigonometric function, right? Where in this inverse relationship, we can approach, right, the derivative results very similar to how we did this with the exponential and logarithmic functions, right? If we consider, for instance, to begin with, just the inverse sine function, right, we might note that y equals the inverse sine if and only if x equals the sine of y. Where if I take the result for x equals the sine of y, and I apply some implicit methods and apply the derivative to both sides of that statement, right, we can show that the derivative with respect to x is equal to the derivative with respect to x for the sine of y, where we know this derivative on the left-hand side is equal to the value of 1, and this derivative on the right-hand side is equivalent to y prime times the cosine of y from our implicit methods. And we're able to say here that 1 on the left must be equal to y prime times the derivative with respect to y for the sine of y, which is where we end up with y prime times the cosine of y on the right-hand side, right? 1 equals y prime times the cosine of y, where if you recall now in our implicit methods, we're going to solve for this y prime by dividing both sides by the cosine of y. And we end up being able to say that y prime is equal to 1 over the cosine of y, right? In the case of our inverse trigonometric function, right? The derivative for y equal to the inverse sine function is equal to 1 over the cosine of y, right? In the context of y and the cosine of y. However, what we do have to realize, right, is that if y equals the sine inverse of x, the cosine of y also must be equivalent to some value in terms of x. And where we obtain that value from, right, since the sine of y is equal to the value of x, what we're able to say from Pythagorean identity is that the cosine of y is going to be equal to plus or minus the square root of 1 minus sine squared of y. And since the sine of y is equal to x, we can say that the cosine of y must be plus or minus the square root of 1 minus x squared. And we can start to think of that being the result that we might find down here in our denominator. However, we do go a little further and note that the inverse sine function, right, this is what we can draw a conclusion of at the current moment. But what we should note is over the domain of the inverse sine function, it is strictly an increasing function. So the negative that could result from having the negative in this plus or minus occur actually will never occur. or shouldn't occur, right? Since y equals sine inverse of x is strictly increasing over values of its domain, values of x in the interval from -1 to 1. So in the end, y prime can end up being said to be equal to 1 over the square root of 1 minus x squared. And that becomes the derivative result that we see for the inverse sine function. The derivative result for the inverse sine is 1 over the square root of 1 minus x squared. Where with implicit methods, starting with the inverse of the sine inverse function, the function x equals the sine of y, through implicit methods, we're able to show that y prime is equal to this quantity down here, 1 over the cosine of y. We're using a little Pythagorean identity. We can narrow that down to say y prime is equal to 1 over plus or minus the square root of 1 minus x squared. Where to finish and to be able to note something about the sine inverse of x is strictly increasing function. So it's always going to be positive, so we're never going to need the negative result in that plus or minus. So in that denominator there, we'll always just have the positive of that result. And thus, this ends up becoming our result in the end. Right? For the derivative with respect to x for the sine inverse of x. And we found it through those implicit methods. Now, a similar result can be shown for the cosine inverse. What we see for the cosine inverse is that we actually get the opposite of what we saw for the sine inverse. It is the opposite of 1 divided by the square root of 1 minus x squared. What we see for the cosine inverse function, it is actually a strictly decreasing function over its domain from -1 to 1. So that's where our negative aspect will come into play. All right. Now that's sine inverse and cosine inverse and their proof. If we look at the tangent inverse next, right, what we can say about y equals the tangent inverse of x is that's true if and only if x equals the tangent of y. So if we apply the derivative operator to both sides of that statement where x equals the tangent of y, we end up with the derivative with respect to x on the left and the derivative with respect to x for the tangent of y on the right, where we're able to simplify the derivative on the left to be the value of 1, as we see in this next step. And this derivative on the right becomes y prime times the derivative with respect to y for the tangent of y, where the derivative of tangent of y with respect to y we know is the is the secant squared of y. So if we take note, we can also say that the above is equivalent to stating 1 is equal to y prime times the secant squared of y, where the secant squared of y is the derivative with respect to y for the function given by the tangent of y. Now, solving for y prime, we divide both sides by the secant squared. And we end up with 1 over the secant squared of y for our value for y prime. Right? Where we do take note on a particular behavior. Specifically, since the tangent of y is said to be equal to x, from the Pythagorean identity, we can also say that then the secant of y must be equal to plus or minus the square root of the tangent squared of y plus 1. And in fact, I think we can even simplify that back to just saying the secant squared of y must be equal to just the tangent squared of y plus 1. And we can substitute that result in to the above statement. Oh, where since tangent of y is equal to x, we can simplify all this to simply be x squared plus 1 for the secant squared y. And now we can substitute that into the denominator for the secant squared y. Implying for y equals the tangent inverse of x, y prime must be equal to 1 over the quantity x squared plus 1. This result here, where for the secant squared of y, we've substituted in the quantity x squared plus 1. Right. This is the inverse tangent's derivative. It is given specifically by the quantity 1 over x squared plus 1. Right? And we draw that result, say, here. Well, we note a similar result can be shown for y, or for the derivative of the cotangent inverse. And actually, let me draw this result for the tangent. This is the derivative with respect to x for the tangent inverse of x. Right? It gives us 1 over x squared plus 1, whereas the cotangent inverse's derivative is, again, now the opposite of that. It is negative 1 over x squared plus 1. The tangent's inverse is strictly increasing, whereas you'll notice the cotangent's inverse is strictly decreasing over its entire domain. And these both have domains from negative to positive infinity. All right? Those are our two results for the tangent inverse and the cotangent inverse, and you can see they're very similar. Now let's look at the secant inverse to finish with. So lastly, if y equals the secant inverse of x, this is true if and only if x equals the secant of y. So if I apply the derivative operator to both sides of the statement x equals the secant of y, we can see again on the left-hand side we're going to end with the value of 1, and on the right-hand side we're going to be left with tangent of x secant of, well, tangent of y secant of y times y prime. We do have to first say that 1 is equal to y prime times the derivative with respect to y for the secant of y. And this is where we get the result tangent of y secant of y. It's from the derivative with respect to y for the secant of y. And we end up with 1 must equal y prime times the tangent of y times the secant of y. We're solving for y prime. Y prime must be equal to 1 over the tangent of y times the secant of y. And furthermore, since the secant of y is equivalent to the value of x, from the Pythagorean identity, we are able to say that the tangent of y must be equal to plus or minus the square root of the secant squared y minus 1. And substituting in for the secant of y the value of x, we can say that the tangent of y must be equal to plus or minus the square root of x squared minus 1. Where this ends up implying at this moment, when we think about substituting in for the tangent, this radical statement, and substituting in for the secant of y, the value of simply x, we could say y prime is equivalent to this quantity seen here to begin with. Now, the secant inverse of x is strictly increasing. So, being strictly increasing, we are going to have to ditch the plus or minus and consider just the plus case. But we also need to control this x's sign and allow it to just be the absolute value of x. And that's what you'll end up seeing in the next statement here. Since the sine inverse is going to be strictly increasing, the slopes are always going to have to be positive. Right? Y prime is going to have to be greater than 0, implying y prime then has to be stated as 1 over the absolute value of x times just the square root of x squared minus 1. We know the result for a square root will always be positive, And we know the absolute value will always be positive, and this will always cause a positive result for y prime. All right. We do see a similar result for the secant inverse. And I'm way off here. Let's fix this. This should be our... Man, I really did miss this at the end, didn't I? This should be the secant inverse of x equals this result. And this should be the case for the cosecant inverse. Again, it's just the opposite of what we see for the secant. Right? It's strictly decreasing over its domain. So we end up having to use the opposite of this statement here we saw for the case of the secant inverse. All right. So those are the proofs for sine, tangent, and secant, and what we can say are there are similar proofs for the cases of cosine, cotangent, and cosecant functions, where the results will always just be the opposite of their cotangent or of their cofunction counterparts for the inverses. Collectively, we can see the results presented here in this theorem, where we also make a little note on when this is true for our values of x, which you have to remember is inverse trig functions are limited for the sine inverse and cosine inverse to be values of x between -1 and 1. For cosecant inverse and cotangent inverse, you have to be outside of, for secant inverse and cosecant inverse, the absolute value has to be greater than or equal to 1. And for tangent and cotangent, x can be any value from negative to positive infinity. And these are our 6 derivative results for the inverse trigonometric functions, the sine inverse through the cotangent inverse function here. Again, they do follow a pattern, every pair, right? Every cofunction pair does follow a pattern. I probably ought to bring this one up here. That would only make sense to pair it here with this one. And then we'll call this item 4. We'll call this item 5 and refer to this as item 6. And we can pair them up as such. Right? And they are very similar in their cofunction pairs. Right? Except one is increasing and one is decreasing in their behavior as inverse trigonometric functions. Now, these are just 6 specific results, folks, where we can incorporate these results into product rules, quotient rules, and even some chain rules. Right. I do have one quick example here. We bring that into view. For example, consider finding y prime for y equals the tangent inverse of the square root of x. Here's a little chain rule. If we let u be that interior function given by the square root of x, that's going to imply y is then the tangent inverse of u. And since the derivative of u with respect to x is 1 over 2 root x, right? That is going to be the derivative. Let me say that's going to be the derivative with respect to x for the square root of x. And this, the derivative of y with respect to u, is going to be our derivative with respect to u for what's going to be the tangent inverse of u, right? Which we know from above is 1 over u squared plus 1. That is this state result here in terms of u, right? So y prime, it's going to be equal to dy dx or dy du times du dx, which is going to be 1 over u squared plus 1 times 1 over 2 times the square root of x for each of these individual derivatives, where since u equals the square root of x, we can substitute in the square root of x here and square it, which is going to simplify to x, and we'll have x plus 1 in the denominator, all times this quantity 2 root x in the denominator. And thus y prime ends up becoming 1 over 2 root x times the quantity x plus 1. All right? It's just a quick example using the results for the inverse trigonometric functions. Here, the tangent inverse function. A little chain rule problem. That chain rule relies upon this derivative result for the tangent inverse in its calculation. That's where it fits into these inverse trigonometric function calculation. All right. The 6 results are stated above, where we had proved the sine case, the tangent case, and the secant inverse case above using implicit methods, as well as some arguments of regarding their behavior, right, to help us determine sine. Right? There's also a little Pythagorean identity in there that helped us along the way. Take note. All right? But these are the derivative results for the 6 trigonometric functions, inverse trigonometric functions. And really what that does is that wraps up the derivative cases for every function type you should be familiar with as a student of pre-calculus, right? Everything from the simple cases of polynomials through rationals up through exponentials and logarithmics, where now we finished with the trigonometrics and the inverse trigonometric functions. We have derivative results for every functional situation that we can encounter coming out of college algebra and trigonometry, right? Where we were introduced to a whole library of functions, and we now have the derivative results for each and every member in that library. And along the way here, what we have done is we have proved every one of those results, or at least have given support for the proof, right? We didn't prove the cosine inverse here, but we did prove the sine inverse and said that it's very similar. All right? So, yeah, we are really at the end here, folks, with looking at specific cases of derivative rules. What I have left to come back and show you, what I might prepare a couple note sets on, are some things where you might appreciate what I have to share about the derivative and its calculation. All right. I got to talk a little bit about logarithmic differentiation. That might be useful. We might come back to chain rule and note it mixed with some of our implicit techniques is going to allow us to generalize some of our derivative results for these different function types. And then what else do we have to say? Maybe a set of notes on nested chain rule. Perhaps I'll develop a little bit of that and have some notes for that, and maybe a quick video. All right. Well, that really does wrap chapter 3 material for the upcoming exam, right, in our class. We did not discuss too much application of the derivative. We've really kept our focus on, we're really just calculating what we might call the slope function, or the value that would describe the slope of the line tangent to our curve. All right. There is a bit more application that is also presented in chapter 3, where I'm going to bring that up and allow that to begin our series on the application of the derivative, and we'll focus our attention on it there. All right, folks. So I probably shouldn't be discussing any of that in the lecture video here, but I am ending the notes there, so the video there. So I will stop with that And I will, I guess, see you in the next one.